In Lesson 5's Launch, Explore, Discuss, Don't Break the Chain, we have a story about an email. Now, if you haven't already read the email, pause the video and read it now. Okay, so some key things that we can pull out of this is that this person sending the email is asking that if you read it, to forward the letter to 10 people. That means send it to 10 people. And if you do that, great things will happen. Now, this next paragraph tells us how our problem is going to be set up. If you haven't already read this paragraph, pause the video. Okay, so the key here is that we're talking about a day-by-day situation. On day 1, you're going to have the letter sent out by Bill to 8 of his closest friends. Each of those friends then sends it out to 10 people, so that by the end of day 2, you have 80 people that have received the letter. We're being asked to find the email on day 7, of course, so understand the pattern, and then day N, so generalize the pattern. So let's start with a table where we have the day and we have the number of people. On day 1, it's sent to 8 people. By day 2, as you can see from the paragraph, it has been reached by 80 people, or has reached 80 people. Day 3, now here's really the key. What kind of a pattern is this supposed to be? Is this supposed to be an adding pattern, a multiplying pattern, or something else? Well, one way to check it is, of course, to look at how far we jump from one day to the next. We jumped 72. Do we really think there's going to be another jump of 72 here? So that by day 3, there's 152 people. Well, that assumes that you're sending it to the same increase every time. But think about it. Each of those 8 people sent it to 10 people. That's multiplication. That's 8, 10 times. So it's not really an adding pattern, then, is it? No. So here's another technique. Take a number and divide it by the one that came before. So 80 divided by 8 is 10. Well, that makes sense because that's how many people the letter was saying to send it to. That would make day 3 10 times bigger than 80. 800. Day 4, 8,000. Day 5, 80,000. Now, let's track the number of tens that you multiply by. So we're going to go ahead and increase this table a little bit longer. This is 8 10 times. This is 8 10 times another 10. This is 8 10 times 10 times another 10. And finally, this is 8 10 times 10 times 10 times 10 times. I left the first one blank. We'll fill that in a minute, but what's the connection between the number of tens and the day? Well, there's 4 10s on day 5. There were 3 10s on day 4. There were 2 10s on day 3. Do you notice what the relationship is there? The number of 10s is 1 less than the day. So let's go back to day 1. On day 1, how many 10s did we multiply by? And the answer is none, 0. We could write that as 8 times 10 to the 0 power, since this is 8 times 10 to the 1. Well, then let's do exponents as we go through. This is 8 times 10 to the 2, and this is 8 times 10 to the 3, and 8 times 10 to the 4. Again, the exponent now is trailing the day by 1. So now we make the leap to generalizing. 6. No. 7. No. N. 8 times 10 to the n minus 1. That n minus 1 is because the day number is always trailing the number of 10s you multiply by. So our formula, back over here, f of n equals 8 times 10 to the n minus 1. And how many people will receive the email on day 7? That would be f of 7 is 8 times 10 to the 7th. No, 7 minus 1. Or 6. If you wanted to write that out the long way, that's 8 followed by 6 zeros. 1, 2, 3, 4, 5, 6. That's 8 million emails. Some people call these pyramid schemes. Where's the pyramid? It's sort of here. Now, as you go on, it's getting bigger and bigger and bigger. Now, a little question. Why can't you write this as 8 times 10 is 80? Why can't you write this as 80 to the n minus 1? Let's think about that for a second. Well, what comes first in order of operations? Parentheses, exponents, multiplying, dividing, sort of on the same level, addition and subtraction on the same level. Exponents are supposed to come before multiplying or dividing. So by writing 80, we've just multiplied 8 times 10 together. But we haven't even touched the exponent. Do we know the exponent? Not yet. We don't know what the number is yet. We just know the relationship is it's n minus 1. So until you know what the exponent is, until you take the exponent, you cannot multiply 8 times anything. So don't do that. Don't write 80 to the n minus 1. Don't multiply those two together. So, what could we say for our takeaway? We can say that when we're doing a geometric sequence, the function value is equal to the first value times the common ratio. Okay, so what is that? What is the common ratio? It's the number you keep multiplying by. So in our table here, in our example, the common ratio is 10. the number that we keep multiplying by. And you notice where the 10 was. The 10 is the base of the exponent n minus 1. So if we're going to write this as a formula, we would write r to the n minus 1. So what does this mean? F of 1? That means the first number. And again, we are making a big assumption. We are assuming that we're starting with 1 as our first number. Sometimes we start with 0. Like, for example, in a race, you might start ready, set, go. On that go, when the timer starts, that's 0. But we're assuming that n equals 1 is where we're starting. That's the explicit equation. That's this one. The recursive would be something like f of n is r times the previous. Now what's the previous? It's f of n minus 1. N minus 1 means the one that came before. These graphs are going to be curves. In fact, sometimes they are called J-curves because they kind of look like the letter J. And they take off really fast. They actually look a little bit more like this. So, key idea today, geometric sequences, how they work. See you next time.